In this next film, we'll take a look at two more examples involving the conservation of energy with gravitational potential energy. We'll take a look at an example, first of all, involving a pendulum. A pendulum is a wonderful illustration of the conservation of energy, and then we'll follow up in a few minutes with an example that examines roller coasters. Okay, now let's begin by taking a look here at this pendulum. Let's consider this point right here, called the equilibrium position, to be height 0. And then therefore, if I do, what this means is that the object right now has no potential energy, nor does it have any kinetic energy, because of course it's not moving. And then let's say that I come along and I do work. I do work against gravity in lifting the pendulum to some height like so, say above the equilibrium position. And now, right now, all of the energy here is in the form of potential energy. And then because the energy is conserved for a pendulum, all of the potential energy here turns into the exact same amount of kinetic energy down at the bottom of the swing at the equilibrium position. And then the process just happens in reverse on the other side of the equilibrium position. All of the kinetic energy here turns into the exact same amount of potential energy over on the other side. This then means that the pendulum will always rise to the same height that it started with, and it will oscillate in this manner forever, as long as we ignore a little bit of friction here between the rope and the attachment and a little bit of air resistance. If we ignore those forces, then ultimately we end up with a situation involving conservation of energy. And then therefore, the pendulum oscillates, for example, like so. Now, where have we seen this before in class, where an object starts at rest at some height and then always returns to its original height? Galileo's experiment that he used to discover the law of inertia. Now, when he did the experiment, he could not explain why the object would always want to seem to return to its original height. However, he did use the result of his experiment to discover the law of inertia. We now know why the pendulum, for example, returns to its original height, and that's because the energy is conserved. So I lift the object like so through a vertical displacement, a height h. I then release the object from rest like so, and then it oscillates in this manner, always returning to its original height. Now, as the pendulum oscillates, you're probably beginning to notice that the height is decreasing with respect to time. And the reason for that is because there's a little bit of friction here between the rope and the attachment and a little bit of air resistance. Those types of forces cause the energy to be lost as heat. Let's go ahead and ignore those forces here. Okay, let's do a numerical example of the pendulum. It's the next example for you to copy down in your notes. Okay, now I'm going to retilt my camera to point it towards the board. Like so. There we go. And now let's go ahead and take a look at the next example. Copy it down in your notes as I read it here. Okay, a pendulum has a length of 1 meter. The string initially makes an angle of 30 degrees with respect to the vertical direction, and the pendulum is released from rest. In part A, we're going to calculate the speed of the object as it passes through the equilibrium position. And then in part B, we'll find the angle made by the string on the other side of the equilibrium position with respect to the vertical direction. In doing this problem, we can then describe the oscillation of a pendulum. Okay, now there is some geometry associated with the pendulum. We first of all draw the situation as seen from the side, that is in profile. Like so. Okay, so here's our pendulum of mass m, and the string has length L that's given to us as 1 meter. Okay, now this right here is the vertical direction, and then this point down here is the equilibrium position, as it's called. Right here is the angle that is made by the string with respect to the vertical direction. This angle here we'll refer to as theta. That's given to us as 30 degrees. Okay, now I'm going to go ahead and draw in some geometry here. We're going to construct a right triangle on this diagram for reasons as you'll see in just a few moments. And then what we do is we take the pendulum here and we release it from rest. So its initial speed is equal to 0. It then moves along a circular arc like so, and it then reaches the bottom of the swing here like so with a speed v that is unknown. This is what we're asked to find in part A of the example. Okay, now when the object moves from here to here, it undergoes a height change. The height change here is h on the diagram like so. We could actually calculate what h is equal to by using the geometry of the pendulum itself, and this is where the right triangle becomes important. Notice that the height change h here is the same thing as the difference between the following two values. This right here is the length of string L, and then this right here is the adjacent side of a right triangle that I've constructed like so, where the hypotenuse of the triangle is L and the angle is theta. This guy right here, the adjacent side of the triangle, we can find by doing a little bit of trigonometry. Let me go ahead and give it a name. I'm going to call it A for adjacent. So let's do a little bit of basic trig. Remember, SOHCAHTOA, specifically in this case cosine. The cosine of the angle theta is equal to the adjacent side of the triangle divided by the hypotenuse L, the length of string. So the adjacent side of the triangle right here, if I cross multiply, is L times cosine theta. The reason why I found that is because the height change h here is the difference between the length of string and A. So then therefore, the height h is the length of string minus the adjacent side of the triangle, which is L cosine theta. This is common to problems involving a pendulum. The height change is always described in this manner. Now we know what the length of string is and then we know what the angle is. So on my calculator here in degree mode, let me just go ahead and find the height change h. So 1 minus 1 times cosine of 30 degrees, and the height change here is about 0.13 meters. Okay, now that I know that height change, let's just go ahead and write down our conservation of energy expression. In this case, we start with all potential energy U. We then end with all kinetic energy K down here at the bottom of the swing. And then recall, of course, that potential energy U is equal to mgh, and kinetic energy K is 1/2 mv squared. And now all that we do is we just solve for the speed v, much like one of the earlier examples that we did in the previous video. Okay, let's go ahead and cancel out the mass of the pendulum like so. And then what we do is we cross multiply the 2 here to the other side, and then we take the square root now to get the speed v all by itself. So after you do those couple of minor mathematical steps, you end up with this expression here, the square root of 2g multiplied by the height change. This will always be the case as long as the object starts from rest and it ends up at a position that is lower than its initial position. The speed is going to equal the square root of 2g multiplied by the height change. We'll see that in the second example involving roller coasters in just a little while as well. Okay, let's go ahead and find this value. Okay, now I still have h in my calculator, so times 2 times 9.8, and then take the square root of all of that. And ultimately the speed here at the bottom of the swing ends up being 1.62 meters per second. And now in part B of the problem, we basically just do the situation backwards. That looks like this. Okay, so now what we'll do is we'll start at the bottom of the swing, like so. With a speed v0 in this case, this will be the initial speed for this portion of the problem, equal to the 1.62 meters per second that we found a few moments ago. Okay, and then right here is the object when it comes to rest, once again like so, for an instant on the other side of the equilibrium position. Here's the geometry of the situation where we have right here the angle theta. This is the length of string L. And then as the object moves from here to here on my diagram, it once again undergoes a height change h. Okay, technically speaking, in this problem, the h is unknown. Once we know what the h is, however, we could use the same geometrical formula to find the angle theta. In other words, once again, h is equal to L minus L cosine theta. But in order to use this formula, we of course have to figure out what h is. It's just the same situation as part A of the problem, but just backwards. In this case, all of the kinetic energy at the bottom of the swing K turns into the same amount of potential energy U here at the top of the swing, like so. So the kinetic energy at the bottom of the swing is 1/2 mv0 squared. This then equals the potential energy at the top of the swing, mgh, and now we just solve for h. So to solve for h, let's go ahead and cancel out the mass m, move the g down to the denominator here on the other side of the expression. And now let's just go ahead and plug in our numbers. So recall that the v0 that we found earlier was 1.62 meters per second. So now I square that in the numerator and then divide by 2 times g. After you do the math here, the value of h comes out to be, no surprise, once again, 0.13 meters. Remember what I said in the demonstration, the pendulum will always rise to the same height as it oscillates, as long as we ignore friction and air resistance. Because the height h here is exactly the same as it was before, that then of course means that the angle theta is 30 degrees. So by using conservation of energy, we can begin to describe the oscillation of a pendulum, as you can see here, quite easily. Okay, now let's immediately move on to the next example, which involves roller coasters. I'm also going to use the next example as a means of giving you a primer on how roller coasters work when it comes to energy transfer. Okay, let me go ahead and do some erasing here first, however. Like so. And then let me go ahead and put the file here on my screen. Okay, there's a diagram that goes along with this problem. I'll draw it in just a moment. A roller coaster cart begins at rest at the top of a hill 20 meters high on a frictionless track. So because the track is frictionless, this then means that the energy is conserved. No energy is lost as heat. Find the cart's speed as it crests subsequent hills that are 15 meters and 10 meters high respectively. So the situation looks like this. Like so, where right here is this initial hill. We have a cart here of mass m, and it is initially at rest. The track itself is frictionless. Okay, and then let's call this hill A. Hill A has a height of 20 meters. Let's call this here hill B. This has a height of 15 meters, and then one of the things that we're asked to find is the speed of the cart here when it's at the top of this hill. We'll call it VB. And then over here is hill C, we'll call it. This is equal to 10 meters high. And then right here is going to be the unknown speed of the cart when it crests this hill. We'll call that VC. Okay, now before we do the problem, which as you'll see is actually quite simple and straightforward, let me give you first of all a short primer on how roller coasters work from an energy transfer standpoint. Okay, now when it comes to most basic roller coaster designs, usually what is the first thing that happens when the train leaves the station? You are pulled to the top of an enormous initial hill. The device that does this is called a chain lift, and the chain lift does work. Specifically, it does work against the force of gravity, thereby giving you a huge amount of potential energy at the beginning of the ride when you're at the top of that initial hill. Usually, you're moving a little bit as well, so then therefore you have some kinetic energy, but by and large, most of the energy that you have is potential energy. And then after that, as the coaster train subsequently moves through the ride, there are no engines or motors or anything like that attached to the train. All that happens is that you start off with a huge amount of potential energy, which then turns into kinetic energy and potential energy and so on as you move through the ride. Of course, there is, in a realistic situation, some friction, so some energy is lost as heat. However, the amount of heat loss is pretty minimal. Usually by the end of the ride, there is a brake that is applied to the roller coaster, slowing you down because you're still moving, usually rather quickly. Okay, now this is what usually happens with most basic roller coaster designs. However, sometimes instead of starting off with a huge amount of potential energy at the beginning of the ride, instead you'll start off with a huge amount of kinetic energy. This is occurring, for example, with a couple of roller coasters that are local. For example, Superman at Magic Mountain, Full Throttle at Magic Mountain, and California Screamin' at Disney's California Adventure. In all three of those situations, what is called an electromagnetic railgun gives the coaster train a large amount of kinetic energy at the beginning of the ride, which then subsequently transforms into potential energy and so on as you move through the ride. So from an energy transfer standpoint, roller coasters, it turns out, are actually pretty simple and straightforward. Okay, now before I do the problem, are you ever going to encounter a situation involving a coaster where you have a hill later on, for example, like so, that is taller than the first hill? And the answer to that question, of course, is no, because of Galileo's experiment. Think of it like this. Remember that regardless of the shapes of the ramps, the object always returned to its original height. So then therefore on a frictionless track, if we start with the coaster cart here initially at rest, that is at this height, it's going to return to the exact same height like so for an instant prior to moving back down to the left-hand side. So then therefore you're never going to encounter another hill later on in a coaster ride that is taller than the initial hill. The only time that you may encounter such a situation is usually on a small scale, and the reason for that is because what the ride engineers would have to do is they would have to engineer into the ride another chain lift that would take you to the top of this hill here, thereby giving you an extra amount of energy. This is usually difficult to engineer on a large scale, so then therefore whenever you encounter a second or third chain lift in a coaster ride, it usually occurs with small rides. For example, some of the rides at Disneyland incorporate multiple chain lifts into their design. Space Mountain, Big Thunder Mountain, Matterhorn, those types of small roller coasters employ multiple chain lifts for this purpose. Okay, let me go ahead and adjust this diagram. Okay, we don't need this, of course, for the problem. So let's get rid of that. And now let's go through this situation, first of all, qualitatively. So we start off here with all potential energy, which then turns into all kinetic energy down here at the bottom of the track. But then as you start to move over the subsequent hills, some of the kinetic energy that you have here transforms back into potential energy, like so, as you move through the ride. Which of the two speeds, VB or VC, is going to be greater? VC is, and the reason for that is because at this hill, you are lower to the ground than this hill. So then therefore you have more kinetic energy and less potential energy here than you would here at the top of hill B. Therefore, as we'll find, VC is going to be greater than VB. Okay, here's then how we go about making this calculation. All of the energy that we start with here is potential energy. And potential energy is mgHa. However, that potential energy of mgHa turns into right here a mixture of two forms of energy. The kinetic energy of the cart, 1/2 m VB squared, plus the potential energy at the top of this hill, which is mgHb. So notice how I'm writing the conservation of energy expression here a little bit differently as opposed to the earlier examples, because when you reach the top of this hill, you actually have a mixture of kinetic and potential energy. But the sum of the two is still equal to all the potential energy at the beginning of the ride because the energy is conserved. And now what we do mathematically is we solve for VB. Okay, so to solve for VB, what I'm going to do is first of all subtract this term to the other side. HA, excuse me, minus mgHb, there we go, like this. Okay, now let's go ahead and cancel out the mass m of the coaster, like so. And then over here on the left-hand side, notice I can factor out a g from each term. So let me go ahead and do that, like so. And then the last couple of steps here now to find the speed VB is to cross multiply the 2 over to the other side and then just take the square root. And then when you do those couple of minor mathematical steps, you end up with this expression here. Notice that this expression here is identical to the expression that we had for the pendulum problem a little while ago. As long as the object starts at rest, when you then try to find the speed subsequently later on at a position that is lower than the initial position, then the speed is described by the square root of 2g multiplied by the height change. In this case, the height change is 20 meters minus 15 meters for a total of 5 meters, and then we multiply by 2g and take the square root. So let's go ahead and do those mathematical steps here on the calculator. 2 times g times a total of 5 meters for the difference, and this then ends up being about 9.9 meters per second. Okay, now we'll set up the same sort of calculation to find the speed at the top of hill C, and as you'll see in just a few moments, the speed is greater than what we just found here. Here's how we'll do, or rather, here's how we'll do the remainder of the problem to find the speed VC. Okay, once again, we're going to write out a conservation of energy expression that is much like this one, except in this case, we're talking about hill C. So all of the potential energy that we start with here, mgHa, that then becomes a mixture of potential energy and kinetic energy here. So it would be kinetic energy 1/2 m VC squared plus potential energy mgHc, like so. So once again, we have two forms of energy that are present here at the top of this hill. Notice, by the way, that mathematically this expression here is essentially identical to this expression. The only difference, of course, is that we're talking about the speed VC. So if I went through the exact same algebraic steps, in this case, as I did a few minutes ago, we would end up with basically the exact same expression, except in this case, it's in terms of hill C. So then therefore, the speed at the top of hill C is going to be described as the square root of 2g multiplied by the height change. In this case, however, the height change is greater than it was in the previous portion of the example. In this case, it's 20 minus 10 meters for a total of 10 meters, multiply by 2g and then take the square root. So let's go ahead and do the math here to finish off. So 2 times 9.8 times a total of 10 meters, and then take the square root. And this comes out to be a greater speed than what we had for VD. This right here is 14 meters per second because once again, we're lower to the ground. So when we're lower to the ground, we have more kinetic energy and less potential energy than we did at the top of hill B. Okay, so with these two examples and the two examples that I did in the previous lecture, we did a total of 4 basic examples here involving the conservation of energy with gravitational potential energy.